So, welcome all of you to this set of lectures which correspond to chapter 8 of your class 11 CBSE book. So, the student should know what chapter 8 is. That is a chapter on gravitation, Newton's universal law of gravitation. So, in the next few lectures we are going to explore and explain various aspects of gravitation as a phenomenon and how Newton's law encompasses a vast variety of phenomena, starting from a falling apple, freely falling body in a gravitational field, tidal phenomena, planetary motion, and even interaction between galaxies, and of course artificial satellites. This is one of the most important topics for a physics student, because this is the first instance of a situation where a fundamental law was discovered, a law governing the properties of all kinds of matter was discovered, and this had far-reaching implications on our understanding of nature, of the very nature of physics, and our approach to understanding what our universe is. And because of that, it also had a far-reaching implication on philosophy. You will not be exposed to all of them in these lectures, for that matter even in your classroom, but it is good to remember that discovery of law of gravitation is one of the hallmarks, one of the high points of the human civilization. So, with this brief introduction, let me get to work. So, what I am going to do is not to start straight away with gravitation, because the very formulation of gravitational law was preceded by major developments in our understanding of the concept of a frame of reference, the concept of a free particle, the concept of a force, the concept of a work, so on and so forth. And I know that both in your classroom and in these very lectures, you have been exposed in great detail to all these concepts. But it does not harm us to repeat these concepts, even if it is done very briefly, because that will prepare us to understand and appreciate whatever we are going to study vis-a-vis gravitation. So, let me first give an outline of what all I am going to cover in this course. The first thing that we shall do is to revise the concepts. So, what are the concepts that we are going to revise? I am going to revise the concept of force, which is fundamental, because we say gravitational force, electromagnetic force, so on and so forth. Then comes the concept of work, followed by two important concepts, kinetic and potential energies, which leads to conservation of energy. So, this is what we broadly call as mechanics. There are a few more things which are associated with it, namely conservation of momentum and conservation of angular momentum, which will also be briefly summarized, revised by me before I get into a discussion of gravitation. Before we start discussing gravitation, it is good for us to remember and realize that gravitation is one of the four fundamental forces. So, we have the concept of a fundamental force, we have the concept of a derived force or an effective force. So, it is remarkable that one of the first forces to be discovered was actually a fundamental force. Therefore, what we shall do is to very, very briefly describe the four fundamental forces, and I have listed them here: gravitation, electromagnetism, nuclear forces, and weak interactions. In some way or the other, you will be exposed to all the four of them. Gravitation, of course, will be described in these lectures, which will be taught in great detail in your class. Electromagnetism, of course, covers a major part of your syllabus in the 12th standard. You will also study a bit of nuclear forces, fission, fusion, etc. And even weak interactions you study in the chapter of beta decay, radioactivity, although you may not be told that weak interactions are responsible. So, in some sense, you are going to be exposed to all these topics. even if these forces are not explicitly mentioned, especially the weak interactions. Therefore, what I will do is to spend some time discussing them after revising the concepts. Once we do that, we can get to the study of gravitation proper. So the first phenomenon that we have to study is the problem of freely falling body in the Earth's gravitational field, and that is the famous Galilean law. So there is a legend that Aristotle believed, or Aristotle propagated, that lighter objects move up and heavier objects come down. Of course, such a thing may happen. If I put a piece of paper, it comes down much more slowly than a heavy object like a stone. But Galileo is credited to have done an experiment from the Leaning Tower of Pisa, where he dropped two objects, let us say gold and tin, or a stone and a block of lead, and they fell with the same acceleration and they reached the ground at the same time. This experiment is very, very important for us because it brings out a far-reaching concept, in fact a very intriguing concept called the equivalence of inertial and gravitational mass. This is a peculiarity of gravitation. So we are going to use Galileo's law to motivate not only the universal law of gravitation, but also the equivalence of inertial and gravitational mass. This equivalence seems very innocuous, very simple, and kind of an accident, but this was the basis of Einstein's generalization of gravity, where he went beyond Newton's theory and gave general theory of relativity. You may have heard of it, black holes, space-time curved and all that. So all of it comes from this equivalence principle to start with. Before I straight away go to gravitation again, what we now do is to look at celestial phenomena. Celestial is what happens in the sky. So what is important for us is to know how the ancient astronomers all over the world, Babylonians, Greeks, Chinese, Indians, they were able to determine distances and time periods of objects in the sky. So you know that eclipses are very precisely predicted, the motion of constellations is known, the period of the sun is known very well, the period of the moon is known. Even the size of the moon, the sun and the earth were estimated to quite a good approximation. Therefore, before we embark on a study of gravitation, it is important for us to know how, even in the absence of laws of physics, people were able to estimate, measure, so to say. So we will start with that. And then again, of course, we have the great tradition of astronomical tables in the Greek and the Indian traditions especially. And we will describe how Kepler was able to analyze the data and give the laws of planetary motion. That is very, very important. There are three laws of planetary motion. So that is something that we need. Newton was extraordinarily fortunate to have been in the possession of Kepler's law. Kepler himself was fortunate that Tycho Brahe actually recorded the motion of the celestial bodies very precisely. Of course, it goes back to very, very ancient times of the period of Ptolemy and Aryabhata. Newton was in possession of all these things, all these data, and he knew Galileo's law of a freely falling body, combining the two, the earthly phenomenon and the celestial phenomena. Newton was able to formulate universal law of gravitation. That is why it is called universal. There is no body in this universe which does not experience a gravitational force, which does not exert a gravitational force on the other bodies. This is a property which is not shared by other forces. So after enunciating Newton's law of gravitation, since we are looking at celestial phenomena, we will look at two phenomena. One, of course, is the motion of the Earth around the Sun and the motion of the planets around the Sun. We will make a simplified approximation that the orbits are all circular for the sake of simplicity. The orbits, of course, are not entirely circular, but it doesn't matter. Then we are also going to discuss the motion of the Moon around the Earth, which is what you have in your syllabus. Now, after discussing these two phenomena, actually for discussing these two phenomena, we will need basic information like mass of the Earth and the shape of the Earth. We come back to the terrestrial gravity, and that is the famous acceleration due to gravity. Many problems which you people have solved. So here, of course, the distance of an object from the surface of the Earth is very small compared to the radius of the Earth. Therefore, g is taken to be a constant most of the time, 10 in SI units, 9.8 let us say. But actually g varies as you move away from the surface of the Earth, as you move on variant points of the various points on the surface of the Earth. So we will discuss that. There are two contributions that are going to come for the variation of g, the acceleration due to gravity. One is the inexact spherical shape. Earth is not an exact sphere, but it is what is called as a geoid. It is flattened at the poles and is bulging at the equator. Therefore, my acceleration due to gravity changes. And the other phenomenon which you are all familiar with is that the Earth not only revolves around the Sun, but it also rotates about its axis, which is inclined at an angle 23.5 degrees, which is very important because that is responsible for the seasons. So that also causes variation in acceleration due to gravity. That is an effective acceleration due to gravity. We have to worry about that. We will discuss that. So in doing that, we will also spend some time to understand the distinction between mass and weight. Newton's fundamental law is formulated in terms of mass. What we measure in Earth's gravitational field is weight. They are not the same. Weight can vary. Archimedes' principle says that weight can change, but the mass cannot change. So we will discuss that. After that, we move on to discuss satellite motion. Of course, Moon is a satellite for the Earth. But today, we have a lot of artificial satellites. We are launching a large number of satellites. Many countries are launching a large number of satellites. And India, our country, is a very major player in that. So you people might have watched on the TV or read in the newspaper that in a remarkable feat, our Indian Space Research Organization launched more than 100 satellites in one shot. Over a period of 10 minutes, it was done. This problem actually involves very fascinating ideas, including conservation of momentum, conservation of angular momentum, and what their masses should be, so on and so forth. I will try to spend some time on them. And then, of course, we have the famous geostationary orbits, which fixes the distance. We will also discuss them. In studying all this, I will also be trying to work out a large number of toy models involving gravitational force, conservation of momentum, conservation of angular momentum, inelastic collisions, breakup of masses and things like that. So that not only will you be comfortable with the concepts, but you will also become more proficient with the technicalities on how to formulate and how to solve problems. So this is essentially the outline of the course. So before I proceed, it is important for us to know what exactly is the impact of gravitation. I told you that it is one of the fundamental forces. I will define what fundamental is in a while, maybe one of the future slides. But in order to understand its scope, you should know that gravitation describes almost everything beyond the Earth, including terrestrial phenomena. So terrestrial means whatever happens on the Earth, falling body, etc., etc. Then it describes planetary motion, So if you look at our solar system, it describes planetary motion. And by the way, in the terrestrial, we should also include the phenomena of tides. Newton was the first person to recognize this, and he actually computed the tides. And we can work out a small problem involving the tides as to how there is a difference in the height. In fact, it is quite interesting because although the moon's gravitational field is much weaker compared to that of the sun. After all, the earth goes around the sun and not around the moon. The moon goes around the earth. But still, when it comes to tidal phenomena, the gravitational field of the moon is much more important than the gravitational field of the sun. So it's a very good thing to discuss. Although I will not be discussing them in great detail, gravitation is responsible for the dynamics of stars. For example, we know sun is producing enormous energy because of nuclear fusion. So the world's original tokamak, the fusion reactor, were all built inside the deep center of the stars. That is how the stars are shining. Now, how is it that such large temperatures and such fusion, the protons and the neutrons can come very close to each other in spite of the Coulomb repulsion? It is because of the gravitational field. Then we have the galactic dynamics. You actually also have the interaction between various stars. Galactic dynamics involves how galaxies are held together or how one galaxy can interact with the other galaxy. And ultimately, we have the large scale structure of the universe. So if you imagine that we know today about 10 to the power of 10 or 10 to the power of 12 galaxies, that is our universe. Every galaxy is like a point in the universe. Then the interaction between the galaxies and how the way our nature behaves is actually described by laws of gravitation. Not entirely Newton's laws, but also its improvement, its generalization given by Einstein, but still the foundations were all laid by Newton. So this is something that we have to remember. So like they say, all the world is a stage. For gravitation, all the world is a stage. So this must be a good enough introduction and motivation for us to start with gravitation. So let us start with a brief review of the basic dynamical concepts. I will not spend any time on the kinematical concepts. So you have kinematics and you have dynamics. Kinematics involves the concept of position, velocity, acceleration, etc., etc. I will assume that you people are familiar with that. I will also assume that you people are familiar with the fact that velocity is a derivative of position, acceleration is the second derivative of position or the derivative of velocity. I am not going to discuss that. So given that, we have to go to dynamics. So what are the three important concepts that we are going to discuss? We first describe Galilean law of inertia, which gives rise to the concept of an inertial frame, which Newton encoded in his formulation of dynamics as the first law. So the first law of motion is actually due to Galileo. The second law, of course, which is fundamental, which is extraordinarily important, is the action of an applied force on a body. Here the emphasis is on the word applied. So we will describe that. And the third law is the famous action and reaction, which actually is a version of what we call as the conservation of momentum. So we will formulate it in that particular way because we are going to use all the three of them. I will not be discussing the conservation of angular momentum at this particular point. It is beyond the course. So we will simply state the principle whenever required and we will make use of them. So we have to start with the concept of forces and inertial frames. Inertial frame is the most important concept, and I know and I am sure that a fair amount of time has been spent on that concept in the earlier lectures in IIT PAL. So please go back to those lectures, listen to them, and again pay attention to these lectures. Two important names that crop up when we speak of forces and inertial frames are that of Newton and of Mach. Mach questioned the concept of an inertial frame, the importance of an inertial frame. I am not going to discuss that at this particular point. But basically, as far as practical purposes are concerned, the foundations for the concept of inertial frame were laid down by Galileo and Newton. This is not to belittle what Mach did. Mach raised many fundamental questions which actually motivated Einstein to develop his general theory of relativity. In fact, he called it the Mach principle, although ultimately his theory was not in agreement with the Mach principle. Okay. So let us start with a few concepts which you people are all familiar with, and that is motion of a body. So here when I speak of the motion of a body, it is good to assume that it is a point particle. Although the conclusions are independent of that, because it simplifies our discussions. So now let us start with the basics of basics. What do we mean by saying that a body is moving? So there is what is called as kinematic relativity. Kinematic relativity. So what does it say? It says that if there are two particles A and B, if B is moving with a velocity v with respect to A, then from the viewpoint of B, A is moving with a velocity minus v. There is no question about that. Similarly, if B is moving with an acceleration A with respect to B, my A will be moving with an acceleration minus A with respect to B. So we call it relative motion, relative acceleration, and this is perfectly symmetric between A and B. It does not involve any concept of dynamics. Now, why is it important for us? We could have simply said all motion is relative, but we know that whenever we want to set a body in motion, that is very important for us. So imagine there is this table and there is this block. In order to set this body in motion, we will have to apply a force. Or imagine there is this road and there is this car going with a speed v. If you want to change its speed or if you want to change its velocity, then you have to apply brakes. Again, a force is required. So whenever we want to change the state of motion of a body, so change of state of motion of a body requires force. So in the first example, the body was at rest. In the second example, the body was in a uniform motion. So what is the problem between the statement that all motion is relative and I require the force? We can look at a very simple example of merry-go-round. All of you have sat on it. In a merry-go-round, you are going round and round about the central pole, but if you look around, it would appear as if the rest of the world goes around you. As if rest of the world rotates. Now, whenever there is a rotation, there is a continuous change in velocity, even if there is no continuous change in the speed, because all of you know that my acceleration is like v squared by r. So, there is an acceleration with the variation of distance, and the direction of speed itself is changing at any given distance. So, the state of motion of the rest of the world is changing, but common sense, our own appreciation of what we understand when we look around us, tells us that the force is acting on us, whoever is sitting on the merry-go-round, but not on the rest of the world. So, in other words, kinematically, although all motion may be relative, but the change of motion caused by the force can be properly described only in some frames. So, change of motion caused by forces requires identification of special frames. And this is not an easy task. For example, if you look at the Greek astronomy and the way it was formulated by Aristotle and later during the medieval period, people assume that the earth is the center of the universe and all the celestial bodies go around the earth. So, earth was considered to be stationary and all the celestial bodies were supposed to go around. Now, if you forget the planets, asteroids, meteorites and even the sun, but you look at the distant stars, fixed stars, then you will see that they all rise at the same time and set at the same time, irrespective of where they are. So, if you make a statement that their state of motion should be because of the force, we would have to say that they are all acted upon by forces such that they all move with a constant angular velocity, which is some kind of a conspiracy of nature. So, this is something which actually worried many astronomers, and one of them was the great Indian astronomer Aryabhatta, who argued that a simpler description would be to say that the stars are fixed, they are not moving at all. It is actually the earth that is rotating about its axis. The minute you assume that it is the earth rotating about its axis, then the circular motion of the stars with a constant period, irrespective of how far they are, acquires a natural description. Of course, we are not saying that Aryabhatta knew what he was saying entirely, because the concept of a force was not very clear at that particular point. But we already see that there is a hint for such a argument to make, and the person who actually formulated this concept in a very precise manner is Galileo. So, let me describe that. I have summarized that in a single line in this slide, the first law for free particles. And what does the summary say? It says that in an inertial frame, no force implies no acceleration. This is very important for us. In other words, we do not infer the existence of force by looking at acceleration. We compute what the acceleration should be by looking at the force. It is very important. So, what are we saying? We assume that we know how to distinguish free particles from others, from the others. So we have to distinguish. How do I distinguish? Because I know that if forces have physical origin, I should be able to find out whether a force is acting on a body or not. Because if I remember the agent that is applying a force, for example, in the spring mass system, it is the spring. In the case of electric interaction, it is the charge. In the case of magnetism, it is the bar magnet. If I remove that, for example, in the case of magnet, my iron rod stops experiencing a force. So I have removed the agency. We assume that we know how to distinguish free particles from the others. Now, once we isolate these free particles, it has nothing to do with their state of motion. That is very, very important. With respect to me, a free particle may be accelerating, but still I should know that there is no force acting on that, because force is caused by a physical agency. It is of physical origin. Once we do that, then we identify special frames of reference, and you have been given detailed lectures on the concept of a frame of reference in this very IIT Paul, and they are called inertial. So what are inertial frames of reference? Inertial frames of references are those frames in which a body which is not acted upon by any force will not accelerate. So that is the statement. No applied force means no acceleration. So what does it mean? So let us make it even more clear. In an inertial frame, no acceleration is equivalent to no force, and this implies uniform velocity. This implies uniform velocity, and what does uniform velocity mean? Magnitude, direction, both are fixed. To an excellent approximation, the Earth is an inertial frame, but if you look at it very, very carefully, you realize that the Earth is going around its axis, and at some point, not in your 12th standard or 11th standard, but later, you will actually find experimental evidence for the rotation of the Earth. There is a very beautiful experiment called the Foco Pendulum, which will tell you that the Earth is actually rotating about its axis. In fact, there are other kinds of evidence like the Coriolis force, the direction of the wind, which blows in the northern hemisphere and the southern hemisphere, which you will study when you study centrifugal and Coriolis forces. There are also other indirect evidences like the path of a river in the northern hemisphere and the southern hemisphere. So there are some evidences, but the direct evidence is because of the Foco pendulum, but that is a rather small effect compared to the revolution of the Earth around the Sun, for example. So it is an inertial frame. If you go out of the Sun and if you sit in a frame in which the Sun is at rest, that is a much, much better example. In fact, Newton, when he formulated his laws, he took a frame of reference in which the stars, the distant stars, would be fixed. That, of course, is not a very good approximation. We know that, very good assumption, because all the stars are receding away. But still, by carefully eliminating known sources of forces, we should be able to get at a good approximation for an inertial force, and I will assume that we are in possession for such an inertial frame, and in that inertial frame, no force implies no acceleration. That is very, very important point. Therefore, what Galilean law of inertia tells us is to interpret a kinematical result through dynamics. And here the dynamics is not by the application of force, but by realizing whether a force is acting or not. So what are we saying? Find a body on which no force is acting, then identify the frame in which it will move with a uniform velocity. In that frame, look at a body which is accelerating and conclude that there must be actually a force acting on it. That is Galileo's great service to science. So that is the first discussion. Now we come to the second law. Second law requires a large number of concepts, which again combines kinematics with dynamics. But apart from kinematics, the second law requires a very, very important concept called the mass. Newton defined it or understood it to be quantity of matter. Which should be distinguished from the concept of volume. So, not volume. This is not a very easy concept, but if you assume that all matter is built out of tiny particles, then it is very easy to see that it is the quantity of matter. So, you take an elementary unit, say let us say that assign mass m equal to 1 to that unit, then compared with that you assign masses to every one of them and you simply count. That is all what you have to do. Now it does not matter what the separation between them is, that will only change the volume, that will only change the density, but it is not going to change the quantity of matter. Therefore, so long as you do not add matter or you do not remove matter, mass is going to be the same. So you can imagine a balloon which is expanding, for example, because there is a certain pressure because of the gas molecules. The volume is changing, the density is changing, but the quantity of matter inside the balloon is not changing. So that is something that we have to remember. So mass is the total matter content. Of course, a big question is, what else does the mass depend on? For example, does this quantity depend on whether that object is at rest or whether the object is moving? Newton declared that is independent of state of motion. What does state of motion mean? That is what I have written in that slide also. It may be at rest, it may be moving, it may be accelerating. In fact, its acceleration may change with time because all kinds of forces are being applied, or for that matter, you may be looking at it from the wrong frame of reference, not an inertial frame. Do what you will, mass is not going to change both kinematically and dynamically. Kinematically is looking at it from a different frame of reference. Dynamically is by keep on changing the forces acting on it. Mass is a fundamental property. So that is the next Newtonian postulate, and we have excellent evidence for that. Nobody says that when a person is driving a car or flying in a plane, the mass changed. If an airline says that you are allowed to carry 25 kilos of luggage, that 25 kg of luggage is understood to be the same whether you are here or flying up in the air at a speed of, let us say, 700 kilometers or 800 kilometers per hour. There is experimental evidence for that, of course. Therefore, we are going to assume that although at some point when you do relativity, special theory of relativity, you are going to violate this and generalize that, but never mind about at this point. Once we got the concept of mass, the next thing that we require is the concept of momentum. So we say there is a great momentum. The body is coming with a great momentum, and generally it is understood when a body is coming with a great momentum, it will have a great impact on us. That means it is coming with a large velocity. But it is also understood that even the mass matters. So at the same velocity, whether it is a housefly that is striking you or whether it is a truck that is striking a hapless person, there is a world of a difference. So we want to characterize the quantity of motion. So the quantity of motion depends both on the velocity and the mass. So Newton, in the simplest of the approximations, rather with the simplest of the assumption, it is not an approximation, declared momentum to be mass into velocity. Declared this to be mass into velocity. This definition is also not changed in relativity, except that this mass will depend on the state of motion. Never mind about that. So now we have the concept of momentum. So what is the statement that we want to make? The statement that we want to make is that mass is not only the quantity of matter, but also it reflects a certain resistance to motion. So if a certain force is required to change the motion of one unit of mass, whatever its state of motion may be, we would like to assume, we would like to believe and then experimentally verify that probably 2 units of the same force would be required to modify the state of motion of 2 sets units of mass in exactly the same state of motion. So we want to have that kind of an additivity, and that is contained in the formulation of Newton's second law. So please remember, Newton's second law does not define a force. What it says is that if there is an applied force, so if you come back to this slide and if you look at it, I have written F applied. That is very, very important for me, because if you say F applied is equal to dP by dt, it makes no sense. It is not an equality. We are saying that F applied is the cause and dP by dt is the effect. It is very, very important for us to know that F applied, applied means there is a physical agency. Somebody is pushing the car, somebody is pulling a rope, somebody is dropping a stone and the earth is attracting it. That is the statement that we want to make. So this is of the physical origin, this equal to dP by dt. So I have the momentum, which is the quantity of motion. That quantity of motion is changed by the application of the force. So what are we saying? This is the cause and this is the effect. It is very, very important for us. Of course, if I am confident that I am sitting in an inertial frame, I can also use dP by dt to infer the applied force, but then I should make a number of experiments to verify that it is indeed because of the applied force. That is the way physics works, and that is something that we have to remember. So far we have carefully enunciated and summarized the 2 laws of motion. Let me repeat them so that it gets fixed in our mind. The first law identifies particles which are not acted upon by forces, and by virtue of that it isolates a special class of frames called the inertial frames of reference. The second law tells us, please sit in the inertial frame, and in that inertial frame if you apply a force, the second law says that then the rate of change of momentum is equal to the applied force. That is what the second law says. So these are the 2 steps that we have. At this point it is good to give some examples of forces because they are needed by us. So let us look at these slides. The simplest example, and with which all of you are thoroughly familiar, I am sure you solved any number of problems, is the spring mass system. The spring mass system for small displacements around the equilibrium position is governed by Hooke's law. F is equal to minus kx, where x is the displacement from the equilibrium position. Then you have the frictional force. I am sure again in your classroom and in these IIT PAL lectures, you solved a large number of problems involving friction. You said that the frictional force is proportional to the coefficient of friction multiplied by the reaction. Then you ask, what is the minimum force required to move an object, so on and so forth. The third force, again, with which you are familiar or with which you will become very soon familiar, is the concept of viscosity. You will do experiments involving Stokes' law. So you drop a small, let us say, a metal pellet, a small metallic sphere into castor oil. In spite of the Earth's gravitational field, after a while, that pellet will move with a uniform velocity, the terminal velocity, because that is due to viscous force. All of you are familiar with the Lorentz force. So what is Lorentz force? Let me write that. Lorentz force. Lorentz force has two components. The first one is the force due to the electric field. The second one is the force due to the magnetic field. Combine them together, this is called the Lorentz force. So this is electric and this is magnetic. So you have already solved these problems. The charged particle goes in a circular orbit in a magnetic field, or you will solve it in the 12th standard. In a uniform electric field, it will suffer uniform acceleration, so on and so forth. And then of course, we have the gravitational force. So I have listed essentially 4 forces. So what are the 4 forces that we have listed? The spring mass system, which is macroscopic. The frictional force, which is again macroscopic. Viscosity, which is macroscopic. The Lorentz force, which is electric and magnetic, and the gravitational force. So if you look at this slide, you see that the last two, the Lorentz force and the gravitation, I have italicized. The letters are slanted because they are of a different nature compared to the first 3 forces. The first 3 forces are not fundamental. If I want to understand spring mass, frictional, viscosity, I have to introduce more elementary forces. Whereas Lorentz force is fundamental. There is nothing more fundamental than Lorentz force. Gravitational force is fundamental and there is a consequence. For example, whenever you have a frictional force or viscosity, your total energy is not a conserved quantity. All of you know that kinetic energy and potential energy will be conserved. Let us say you want to make such a statement. They will not be obeyed by viscous forces or frictional forces. That does not mean energy itself is not conserved. There are other forces, there are other objects which we are not taking into account. If you take all that into account, then there will be a conservation of energy. But gravitation and Lorentz force are in a different league, they are fundamental. So when we do that, the total energy or the total momentum or total angular momentum should be a conserved quantity. So these two are of a different nature, of a different category compared to the first 3. Or for example, if I go back, when I look at the spring mass system for small displacements, so let me write them down here and that will make the concept very, very clear. So let me look at spring mass system. So if I write a force, I will write minus kx, but this is valid only for small displacements. So if I stretch the spring a little bit more, it can pick up a term like minus k prime x cubed, etc., etc., etc. So in other words, depending on what kind of a displacement I give, the force law keeps on changing. So that is why it is not a fundamental force. In a similar manner, if I look at viscosity or friction, It can be constant for small velocities. That is what you assume when you solve the problem of a block moving on a rough surface. It can be proportional to velocity. In fact, at very, very large speeds, it can be proportional to v squared. For example, if a jet plane is going. Therefore, again you see that the form of a frictional force or a viscous force or of a spring mass system depends on what your displacement is, it depends on what your velocity is, it keeps on changing. But when you look at Lorentz force or gravitational force, they are not going to depend on anything. They are valid at all distances, they are valid at all velocities, at all momenta. That is the most important thing. And that is the reason why we say that spring mass system, frictional force, viscosity, etc., they are all derived effective forces, whereas Lorentz force and gravitation are fundamental. There are other fundamental forces. Now, I move on to the formulation of the third law. The third law is a very important law for us because in the second law we only look at the applied force and we made a distinction. So, let me write that down. So, this is where you see the genius of Newton. In second law, there is an asymmetry. So, I write F applied is equal to dP by dt. This is the agent, cause, and this is the effect. So, I say the earth, and this is a ball which is freely falling. There is an asymmetry because earth is causing the ball to move, and I am interested in the motion of the ball because of the earth's gravitational field. I am not worried about whether this ball is acting on the earth or not. So, Newton's second law in some sense would be valid if a body A applied a force on a body B, but body B did not reciprocate. Such things happen in nature, in real life. So, there are a lot of such interesting statements like A would like to be the friend of B, but B would not like to be the friend of A. There need not be a symmetry of that particular kind, right? These are relations. A is related to B in a particular manner need not imply B is related to A in the same manner. It could be a different thing. But the third law of Newton establishes a symmetry, and it establishes the symmetry in a very beautiful way. So, what does it say? I have a body A and I have a body B. Now, when I say that A acts on B in a particular way, and I am going to write it as F A cross B. Remember, velocity, momentum, acceleration, force, angular momentum, they are all vectors. So, I will put it in this direction. Now, let us say that I do not look at B, but I look at A, and I ask what might be the force acted upon by B on A. I can ask such a question, and I will write F, I am sorry, here it should be, this is correct, A acting on B, here F B acting on A, and here it is F A acting on B. So, what am I saying? The change of momentum of B is because of the action of A, the change of momentum of A is because of the action of B on A. Newton's third law establishes a fundamental relation. Qualitatively, Newton's law tells us that if A acts on B, B should act on A. It cannot be a one-way interaction. It cannot be a one-way deal. It is not possible. But over and above that, it says that the force of A due to B is equal to negative of force B to A. Okay, this vector sign must be on the force, not on the particle. I am sorry about that. So they are negatives of each other. This is very, very important. They are equal in magnitude, but they are in opposite direction. So if you did that, there is a simple exercise that I would like to leave you with. And what is that exercise? I don't want to work that out. And that is, if you go back to this slide for a minute, I have written an equation. So please look at that slide. And what does that slide tell you? It tells you that dP1 by dP2 equal to 0. Okay. There is a slight notation mismatch. P1 is the momentum of A, P2 is the momentum of B. The third law tells you that the total momentum is a conserved quantity. So please take this as an exercise, work it out. Then if you are comfortable with that, we had laid down the foundations for discussing the universal law of gravitation, which I will take up in the next lecture. So thank you, have a good day.